thank you, Manu. Thank you, Mike, for inviting me here to present the award for Innovator of the Year to a very special faculty member that we're really proud to have in the College of Engineering and, of course, at Boston University. This year's Innovator of the Year is Professor Jishin Zhang. Jishin was recruited from Purdue University to Boston University in the summer of 2017 as the Moustakis Professor in Photonics and Optoelectronics. He holds a joint tenure appointment in electrical and computer engineering and in biomedical engineering. He's received many awards, including the Ellis Lippincott Award from the Optical Society of America. He's an elected Fellow of the Optical Society of America and the American Institute of Medicine and Biological Engineering, AMB, and the Craver Award for Koblenz Society, just to name a few of his awards. Since arriving at BU, he has demonstrated himself as an innovator of high productivity, exceptional creativity, and an outstanding entrepreneurship, and a fantastic scientist. He's published since 2018, it says here, I even don't believe it, but it's true, 92 peer-reviewed articles, 6 in Nature Communications, 5 in Light Science and Applications, 5 in Science Advances, 2 in PNAS, all as senior author. He's been cited over 33,000 times with an H-index of 93 in Google Scholar. But he's far more than a scholar only. He is a prolific inventor. Michael Pratt, the Managing Director of BU's Technology Development Office, OTD, indicates that when Professor Zhang visits his office, he's not just making a disclosure for disclosure's sake, but rather he has a practical application in mind and many times has a research sponsor or a business in mind. His creative work has generated 10 patents, and these IPs span the areas of chemical imaging, neuromodulation, and antimicrobial phototherapy. Several of his patents have been licensed to multiple companies and converted into products with a measurable societal impact, and I'll give you some examples. In chemical imaging, his US patent on deep learning, polygon scan stimulated Raman spectroscopy, microscopy, has been licensed to Vibranex Incorporated, co-founded by Jishin and a former student, Pu Wang. Vibranex Incorporated generated sales of over $5 million in 2022. Using a successful SBIR STTR grants, his multiple BU IPs on infrared photothermal imaging have been licensed to Photothermal Spectroscopy Corporation, for which he is the Chief Scientific Advisor. Since its inception in 2018, Photothermal Spectroscopy Corporation has delivered 45 units of MI-RAGE, an infrared photothermal microscope, to 8 countries: the United States, Canada, France, Germany, UK, Japan, Korea, and China. One example of application of this is mapping protein aggregation in Alzheimer's disease. He has created 2 new directions since coming to Boston University. One on a genetics-free neuromodulation through an optoacoustic effect, and another on an antimicrobial phototherapy. Jishin and collaborator Chen Yang invented a fiber-based optoacoustic emitter that allows sub-millimeter precision ultrasound neuromodulation. This optoacoustic neuromodulation IP, pending US Utility Track 1, has received broad industrial interest. For example, Axeris, if I said it correctly, a company located in Paris, recently licensed this IP for retinal stimulation at an unprecedented spatial resolution. In antimicrobial phototherapy, Jishin and co-workers invented methods to treat the superbug MRSA. He's invented and generalized approaches to treat drug-resistant pathogens by photoinactivation and co-founded Pulsethera, I have no idea if I said that right, which aims to commercialize this approach to treat broad category of infections, including MRSA, Candida, ERS, that impose a huge threat to human health. Dr. Jishin Zhang is a textbook example of the values and processes that lead to successful entrepreneurship, and the kind of convergent scientist and societal engineer we want on our faculty. So congratulations to Jishin, and let me offer you.
thank you. First, thank you all being here today for me. First, I will thank my current and former students, postdoc, my BU colleagues, and my family. This is not possible without strong support to me. My name, Ji Xin, exactly means continuous innovation in Chinese. So today I'm going to spend 10 minutes to tell you how continuous innovation happens to Ji Xin. So I'm a Chinese. In the Chinese philosophy, the universe is driven by interforce between yin and yang. And a word to describe this world is change. So in my view, no fear to change is a foundation for innovation. And innovations are often driven by the opposite in this yin and yang picture. In 2003, I was trained as a physical chemist in Harvard, and I just got a very good offer from a very pretty decent chemistry department. Then I got this very special offer from Purdue University, biomedical engineering. I had no idea what is biomedical engineering. I talked to Sonny, and my advisor, he told me, they make artificial bones. But in the end, I accepted the Purdue offer because I said, I want to do something different from you, from chemistry. And it turns out that's a very good decision because I was able to bring spectroscopy into the engineering discipline. And that helped me to grow a new field called chemical imaging. Actually, this year I just launched the first Golden Research Conference on chemical imaging. But teaching has been a difficulty for me in engineering, right? So I was fortunate to have a very capable father-in-law who can teach me electronics before I go to class. But that creates opportunities. So this is one example. In one of the lectures, I teach this a cascade of LC circuits to model the cochlea. So each circuit is amplified by one frequency of sound. So that's why we can hear all frequencies of sound. We borrowed this idea from the undergraduate class to my research and built a 32-channel tuned amplifier array. So here each board can amplify this called a stimuli-Raman signal at one frequency. This creates actually the fastest Raman spectrometer in the world, 5 microseconds per Raman spectrum. This got me 2 US patents and actually finally a science and engineering grant from Keck Foundation. But there are also other barriers for translation of clinical translation chemical microscopy, the limited imaging depth into tissue. In 2007, I was using cars to image cardiovascular disease. And we can see this beautiful plaque, but we have to cut the artery to see through the cross-section because cars microscopy, which is my major work as a postdoc, only has a penetration depth of 100 micron, and that is not possible to do in vivo detection in the hospital, right? So other groups are using adaptive optics, but that only increases 2 to 3 times. So that time there's no way to break this barrier because we need a millimeter imaging depth. An idea came to me in 2009. So at that time, at that year, my wife and I expecting our first child. And we had to go to the hospital every month to do ultrasound because the doctor suspected some water in his kidney. But the boy is okay, he's taller than me now. So, but at that time, I was super impressed by this ultrasound image. It can go that deep, my goodness. And it can see through the whole body. But I was a physical chemist, I'm still a physical chemist, and I knew that after vibrational excitation, all the energy will go to heat. And if we use a pulse excitation, we can produce a transient ultrasound to generate transient heat to produce an ultrasound. The difficulty is that we knew nothing about ultrasound or photoacoustic research in my team. So I invited Li Hong, who was a pioneer of using PI to do blood, to Purdue to give a seminar in biomedical engineering. And then I convinced him that I can send a student to the first author of this paper to his lab to learn the very basics of photoacoustics. In 2011, we published this paper, a new way of bound selective imaging by listening to vibrationally excited molecules. So this can go deeper as a few millimeters. This method allowed for the first time that we can see the lipid-laden plaque from the lumen side, and this built the foundation for in vivo detection by through a caster. This paper also saved my mid-career because at that time I was never able to renew my R1 on cars, my microscopy. But this new data allowed me to get an R21, R1 National Innovation Award and a recent renewal of the R1. In 2014, I co-founded this Brown Inc. with my former student Pu Wang, who is now CEO of the company. And we have a dream. The dream is to convert that method into a device to really for in vivo detection of this vulnerable plague, the #1 killer in the United States in a human. Then we realized that it's 100 times more difficult to make a clinical product than just publishing a paper. But the Vibronics now is already a 30 people business, and we made other FDA approval device for other simpler purpose. And last year, the Vibronics produced a sales of 30 million Chinese yuan or $5 million in 2022. In research, we fail most of the time, as we know that. But the wisdom tells that the weakness can become a strength if you look at the same data from a different angle. In 2017, we are using this transient absorption microscopy to image the detect the MRSA by imaging the golden pigments. Initially, the signal is very strong, but then in 0.5 seconds, the signal completely disappeared due to photo bleaching. So this is absolutely a failed project from an imaging and diagnosis perspective, right? But we did not stop here. Instead, we asked a different question. We asked, like, can we kill MRSA this way by bleaching these golden pigments? It turns out that's indeed the case, because these pigments called STX result in membrane. So if we break down the molecule, we can make the membrane leaky so that the small molecule like hydrogen peroxide can go into the cell and kill the bacteria. The Brink reported our finding in 2019, and many people read the news and they write to me because there are many MRSA patients. And in November 2019, a guy from Colorado wrote to me with some astonishing data. He had a MRSA infection, and antibiotics did not work for him for 3 months. He was desperate, and then he followed our product on mice. That's our paper did on his arm, and the blue light plus hydrogen peroxide saved his forearm in 3 days. In the same year, we founded a Pulsera to try to aim to convert this into a medical device or broader patient use. While I'm playing just different projects for fun during the year, driven by curiosity, my major research is focused on bound selective imaging. Since my postdoc work on cars, microscopy in 2000, we have a dream. The dream is that we want to have a method to visualize the interaction, how molecules talk to each other inside living system. This is beyond the capability of fluorescent microscopy. If we use a chemical bond, we can give the right information. But the difficulty is that we don't have enough sensitivity. Both CARS and the stimulated Raman scattering microscopy, for which I'm a co-inventor, are only sensitive to CH bond species such as amino acids, lipid, cholesterol in cancer. But most molecules, such as drug molecules, carbohydrate, RNA, they work at a much lower concentration, from micromolar to nanomolar level, right? In 2015, when I was invited to write this review article, I started to ask, what is the fundamental limit of this field? And it's the physics. This Raman scattering has a very small cross-section, and this limits the ultimate detection to a minimal level, no matter what we do in instrumentation. Outside the Raman box, we found a mid-infrared absorption, which has a much bigger cross-section, and it is even bigger. Recently, we did a DFT calculation through collaboration with my colleague in chemistry. We found for certain group like azide bond, the cross-section is as large as fluorescence, but it's 14 orders larger than Raman scattering, and that creates a tremendous opportunity. The difference is that the fluorescence has emission, but after infrared excitation, we have no photon emission, but it produces heat. So this is the idea that in 2016, we published a new microscopy called a mid-infrared photothermal microscopy, which we use a mid-infrared laser to induce a temperature rise and change the local refracting index. Then we use a green probe this photothermal effect by measuring the change of refracting index. I would say that while the first paper was from Purdue in 2016, it is at the Boston University in this building on the 8th floor that we fully substantially developed this technique that shows these papers, and this has been licensed to this photothermal spectroscopy. So in October, one thing I want to mention that this is, we are not alone in this, that this is through the collaboration with my colleagues, Selimi Anlo and Lei Tian, and we are not alone in this direction. My other colleagues, Sean and Michelle, also developed photothermal spectroscopy, but from a different perspective. The story is that in October 2016, I gave this speech in the science meeting. And I was lucky that time because the leaders of analysis were in the audience. And after my speech, they asked me for a coffee. And during the coffee, they told me that you want to convert this paper into a product. In April 2018, Mirage was announced. Mirage is a very good name because Mirage means that the contrast is from the change of refracting index. After this analysis was sold to Bruker in 2019, we formed photothermal spectroscopy Corp to commercialize our technique at full speed. And till now, that the Mirage has been delivered to 70 research labs in 8 different countries and created sales of $10 million in 2022. So this has allowed much broader application of the technique that is far beyond my own research lab. Now my final slides. There are many potential applications of this technique, and we are working on one. It's called a click-free MIP image in the silent window. So the idea is that we can now use a special chemical bond, such as azide or the nitride group, only 2 atoms as a GPS of molecules to track the molecule and to understand how the molecule talk to others in the cell. In 2022, the Nobel Prize in chemistry went to click chemistry. In this method, the azide tagged sugar enter the cell and they build the cell wall. Then a click reaction is used to conjugate a fluorescent dye like rhodamine into this molecule for visualization. However, because the click chemistry fix and change the molecule, this method can only take a one snapshot of the molecule at one time. But now, by our method, we can directly visualize this GPS, this azide molecule, so that we can visualize this, the molecule we want to study, like in this case, azido trihalose, in real space, real time, see the dynamic pathway, the metabolic pathway, and we also have data showing that we can study how this molecule interact with other molecules through vibrational spectroscopy. So after 20 years effort, I believe that we are on the right track to turn the initial dream into reality. And with this, I thank you very much for listening, and thank you for being here today.
Thank you, Shijin. Congratulations. And thank you, Rana, and the faculty panelists. I really enjoyed those comments. I hope we can have a reception now and talk to each other and hopefully share some of our thoughts and create more innovation. Right? This is what's supposed to happen. So make a few inventions, a few more disclosures, send them our way. All right. Thank you, everyone. Congratulations, Shijin.